Hello and welcome to my submission for exam 2. In this video, I'm going to be defining a certain system where we have some nodes and pipes between the nodes, and then I will find the flow rates between each node, and we'll find the net flow for each node. And so I've drawn a picture here of our system. We have 5 different nodes starting from node 0. We have a source node and we also have a sink node. At these 2 nodes, it doesn't matter what the flow rate is, or the net flow I should say. We're allowed to use those nodes in any way we need, and then our internal nodes here, 1, 2, and 3, all have to have net flows of 0. So we're going to be doing most of our work through the Bernoulli equation, and then we also have an equation called the Churchill equation, which is going to allow us to find a friction factor to use for our Bernoulli equation. And then we also have some given values for the pipes. We have the lengths, the number of fittings on each pipe. We know the elevations of our nodes, and we're also given the external pressures of our nodes, so the pressures on node 0 and node 4. And then we also are given the diameter and relative roughnesses of our pipes. And so to start off with, first we will define a function to solve for our friction factor, so our Churchill equation here. Actually, we'll go ahead and list out all of our given variables first. So first import numpy, and then we can import 2 equations, optimize. We'll import 2 functions that we need to, we'll use them later on, I'll explain them later, but it'll be a Newton function and a roots function. And then we can list out some of the given variables that we will use throughout these calculations. So we have our gravitational force, we have the density of water, we have the diameter of our pipes, we have the relative roughnesses of our pipes, and we know the viscosity of water. And we're assuming that we're using water in this system, so viscosity of water. And so we first want to define a function to solve for our friction factor. So we'll just call it f. We need to give it a Reynolds number and a relative roughness. And so this function is working on the fact that we're giving it, or that we have some sort of flow. And so we know that we have A and B. So A is A, we have B, and then we'll return this part here, which is our fanning friction factor. And so we have A is being equal to 2.457 times the natural log of 1 over 7 over the Reynolds number, so 7 divided by RE, the power of 0.9 plus 0.27 times the relative roughness, and that is all to the power of 16, I believe. Yep. And then for B, it's just 37530 divided by the Reynolds number. And we want to return our fanning friction factor, which is 2 times this quantity, so 2 times 8 divided by the Reynolds number to the power of 12 plus 1 over A plus B and A plus B is to the power of 1.5. And then this is all to the power of 1 over 12. Okay, so we have our friction factor, and from here we can find our change in head. So we'll define a function called dhead, and we need to give it the parameters of our pipes in our systems. We also need to give it a flow rate, so Q, and then the length, the diameter of our pipe, number of fittings, and our relative roughness. And as we look at our Bernoulli equation, we know that the left side here has to be equal and opposite to the right side of our Bernoulli equation because it's all equal to 0, right? And so if we look at the right side of our equation, if we're given a flow rate, we know everything on the side except for the fanning friction factor. We're making a guess for that friction factor. Actually, no, sorry. If we have a flow rate, we can find the fanning friction factor. And so we can actually just return this side here, including the negative, and that is equal to our change in head for the system. And so we have our flow rate. First, we need to turn the flow rate into a velocity. So the velocity is the flow rate over the cross-sectional area. So it will be 4, because we're working with a circular cross-sectional area. So 4 times Q divided by pi d squared. So the velocity, and then we need to find a Reynolds number to give to our fanning friction factor function. So the Reynolds number, of course, is equal to rho v d over mu. So rho v d over mu. And then we can return the right side of our equation here, right? Because we have K, we have our fanning friction factor that we can calculate, we have LD, and we just found V. And so we can return negative K plus 4 times the fanning friction factor. So we'll use our function that we just defined, times L divided by D times V squared divided by 2 times G. And that's our change in head, because again, if we return the negative value of this side, we have the magnitude of our change in head, right? And so now that we have our change in head, we can start to develop a function that will define our flow rate. So we'll just define flow here. And eventually we want to return, right, the resulting flow rate. And how can we find this? Well, we know if we look at our Bernoulli equation here, we have most of these variables that we know, right? But we don't know necessarily V because we haven't been given a flow rate for any of these pipes yet. And if we don't know V, we don't know our fanning friction factor either. But we know most of these other values because if we see here, the left side is equal to the right side, and we're returning the right side, right? So we can find our delta head using this equation here, our change in head, because it's returning this side here. And then we also can assume that we're given a delta head, and we can solve for the delta head later. But if we know a delta head, and then we can return this side of the equation, we know that they have to be equal and opposite to each other. So we know that the difference has to be equal to 0, right? So we could say, we can define a function that will drive the difference between these two sides to 0 by varying one variable. And so what we can do is we can make a guess for either our flow rate or our fanning friction factor. And then from that guess, we can allow our script to vary its value until we've satisfied our Bernoulli equation, until we've satisfied the fact that this has to be equal and opposite to this side of the equation. And so we'll define this function that will drive to 0, f to 0. And we can either give it a flow rate or a pressure to vary. And if we were to give it a flow rate, well, we don't know the flow rates yet. The flow rates could be anything, but we need to give it a flow rate or a pressure to make a guess of, right, to vary. So if we're looking at, if we wanted to make a guess for our flow rate, well, it would have to depend on our friction factor here, because flow rate, of course, depends on the friction factor. And we can make a reasonable guess for the friction factor because the friction factor can't vary all that much. But we can't really make a reasonable guess for the flow rate if we don't assume we know the friction factor. And so if we were to say make a guess for our flow rate, well, first I'll show how this function works. So we're driving an equation to 0 or function to 0. In this case, we're driving the difference between these sides to 0, right? We're driving this plus this to 0. And so to do that, all we have to do is use our Newton function, and we need to give this Newton function, first of all, a function to drive to 0, and then we need to give it an initial guess for that function. So if we have a function of x, we have to give it an initial guess of x to then vary until it finds the zeros or the roots of that function. And so if we are going to work with a function called f to 0, and we're giving it a flow rate, we need to have a guess for the flow rate so that we can vary this function to 0. And so what we can say is we can have a guess of our function, or a guess of our flow rate, and this flow rate's guess will have to depend on our delta head, of course, right here in our numerator, and then it will also depend on the friction factor down here. And so the friction factor only varies from 0.002 to 0.025, and so we could just make a guess of 0.01, and it's not going to be exact, of course, but it will be a reasonable guess, and then we can vary the flow rate based off of that original guess. But it would make for a reasonable guess. So if we solve our Bernoulli equation for the flow rate, then we'll find that we have all the values that we need to solve for a reasonable guess of our flow rate. So the flow rate, Q, is equal to the pi d squared over 4 times this square root. So pi d squared divided by 4 times the square root of, and then we have our negative delta head times 2 times g on top, right, because this is our negative delta head, and then it's divided by k plus 4f times L over d. So divided by k plus 4, and then f here, well, we have to make a guess for our friction factor in order to have some numerical value for our flow rate. And so this is where we use our guess of 0.01 times L over D. And we're given L over D for each pipe. And so this is a reasonable guess for our flow rate. We can then use this guess in our f to 0 function. And of course, this f to 0 function is returning the difference between the left and right side of our equations here, right? Well, we can find this value here because we already have a function to do that. And if we use this function to return this side, then we can subtract the delta head of our system, which is this side, and then we can drive that to 0 so that these two sides are equal to each other. So we can return delta head, and we need to give it all of the values that we need to give the function up here. So the flow rate, the length of the pipe, the diameter of the pipe, fittings, and relative roughness. And then we want to subtract the delta head of our pipe, right? And then what we can do is we can define this initial guess, and then we would be given a flow rate if we drove it to 0 based off of our initial guess, right? And so this would give us a flow rate for a specific pipe as long as we know the pipe's delta head. And so we can use all of this in our flow function. Flow. And then we need to give it a guess for our flow rate, which is qguess down here. And then we need to we need to first drive this to 0, right? And so we can say resulting flow rate is equal to, and then we will drive it to 0 by giving it our initial guess for the flow rate. And then we can return our resulting flow rate. And so we do have two problems with this function here, and we also have a problem with this function above here, actually. So here we're given a flow rate, and then we are changing that flow rate into a velocity. And of course we can have a negative flow rate, that's fine, just depending on how we look at the system. And we can have a negative velocity too, but what we can't have is a negative Reynolds number. And this function here is giving us a negative Reynolds number for a negative flow rate. And we don't want to work with that, so to simplify things, we can just we can take the absolute value of this here. So no matter what flow we're given, we'll always have a positive velocity. And then when we do that, we get rid of the directionality of our function here. So say we're given a negative flow rate, and we throw it into this function, well, our function is going to calculate it as if we had a positive flow rate, and it would then return to us always a positive value for the delta head, or I guess a negative value for the delta head because we have a negative sign down here. So we need to reincorporate the directionality that we had initially that we just got rid of. So what we could do is multiply by the sign of our initial flow rate up here. And so no matter what, if we have a positive or negative flow rate given to us, we can always find a suitable Reynolds number and then always return a suitable change in head. And then here we have a similar problem. Well, first we need to give this function some of the values that it needs. So it needs a delta head, it needs the parameters for our pipes down here, so L, D, K, and then the relative roughness. And then in this system, we could have a negative delta head as well, and that's fine. It's similar to our flow rate. It just depends on how we look at our system. But we're not going to be able to solve this with a negative delta head. Our function isn't going to like that. So what we can do is just define a new function, define a new variable called delta head absolute. So the absolute value of our delta head, and it's just going to be the absolute value of our delta head. And then we can use that absolute value of delta head throughout our function here to make sure everything runs smoothly. Okay, and then to reincorporate the directionality again, what we can do is just multiply by the sign of our original delta head down here when we return everything. And so this way we don't have to worry about our system not working with any negative delta head values, and we can still take into account the possible negative delta head value when we return the flow rate. And then another problem that we're going to have is we'll eventually be varying our delta head and varying a couple different variables, and we're going to try and get some values to converge to 0, just like we tried to converge our Bernoulli equation to 0. And we're not going to get exactly to 0, but what we can do is say that if the delta head is almost 0, so like less than 1e to the negative 10, we can go ahead and assume that it's equal to 0. So now that we have a function that will find the flow rate for our pipes, we can go ahead and actually model out our system. So I'm going to make an array for our pipes, and we'll just give a we'll have a array of pipes, and we'll give the node that the pipe is coming from, the node that it's going towards, and then we'll have the length of each node and the number of fittings on, the length of each pipe and the number of fittings on each pipe listed in this array. So, and then we'll have one row for each pipe in our system. So we can say an array, and just to make it easier to see, we'll first list out we'll call this from node, so the node that the pipe is coming from, and then we'll call them to nodes, so the node that the pipe is going towards, and then lengths, that's our L value, and the number of fittings is our K value. And so once again, we'll have a list in each row, and each row is going to be representative of one pipe. And so for our first pipe, it's from node 0 to 1, so 0 to 1, and then it has a length of 1.5 and 1.5 fittings on it. For our second pipe, it's from node 0 to node 2. It has a length of 2 and a K value of 2. For our third pipe, it's from 1 to 2 and a length of 1.5. And a 0 K value. And then from 1 to 3, length of 1.5, same K value. So 1 to 3, 1.5, 0. And then we have a pipe from 2 to 4 with a length of 0.5. So 2 to 4, 0.5, and then again a K value of 0. And then our final pipe is 3 to 4 with a length of 3 and 2 fittings on it. So 3 to 4, length of 3, and a 2 K value. And then we have 6 pipes. Okay, so now we want to list out all the information for our system, and a lot of this is given to us, and then some of it we can kind of derive from our list here. So first we want to give a list of our heights of each node. So we can say, this is given to us, we'll just list it out. So we have the first elevation, the elevation for the first node is 30, and then the rest are all 0. So we have 5 nodes, And then we can list the external nodes as being nodes 0 and 4, and we can list the external pressures as being, again we're given this, so 2e to the 5, so 200,000 pascals, and then 0, so the source node has a pressure of 200,000 pascals, our sink node has a pressure of 0. And then we can create a list of all of the given values here. So we can create a list of our from nodes, and this is just going to be an array, and we're calling, so the from nodes of course is just all the information in our first column, so pipes 0. And then we can do the same thing for our two nodes, as it's just everything in our pipes array in the second column. And then we can list our lengths, so we'll call the list lengths, and it is equal to, again, same thing as the previous two, everything in our third column. And then we can give our k values as well, so k is equal to, again, the same thing. So everything in our fourth column. Alright, so we could also give the number of pipes in our system, so we'll call it n pipes. And to do this, first of all, we can make use of our shape function for an array. So we have our pipes array, and then say we want to know the shape of it. Well, it returns to us the column, or the number of rows and the number of columns, the number of rows always being the first element in the list that it gives us. So if we were to add pipes to this system, we would be adding rows. We wouldn't change the number of columns, but we would be adding rows. And so to make our script pretty durable and allow it to work if we had more or less pipes in the system, we can make use of this shape function. So we can say number of pipes is equal to the first element in our pipes.shape function down here. And so what this is basically saying is, well, we know that we have one row for each pipe. So if we have one row for each pipe, we can count the number of pipes by the number of rows in our array. So we can say pipe in pipes, and it should give us, yes, a 6, because we have 6 rows and 6 pipes. And then we can also we can calculate the number of nodes, and we can do this because we know, actually before we do that, we can give the information for our pipes. So we can create a list of the diameters of our pipes and a list of the relative roughnesses of our pipes. So we can call pipes D, and then we have already defined the diameters of our pipes right here as 0.1. So they're all the same, so we can make a uniform list of whatever the size of the number of pipes we have is, and then call them all the same variable D. So we can say a full list, and then we need to give it a shape. So n pipes is the shape of 6, a list of 6 elements, and then they all need to be D, so they all have a value of 0.1 for their diameter. And then we can also do the same thing for the relative roughnesses for each pipe. And then now we can also find the number of nodes in our system, and the number of nodes in our system is going to be the largest value here in this second column, right? Our 2 nodes plus 1, because we're starting our indexing at 0. So we can call, again, if we were to add nodes or pipes to the system, we could call just the largest value in our 2 nodes list. So we could say max, and here we could either simply call the largest value from our 2 nodes list that we've already defined, or we could call the largest value just in the second column. And so we'll just do the latter. So we'll say the maximum number in our second column of our pipes array. We want to store it as an integer. And then we want to add 1 because we start our indexing at 0. And then actually for the nodes lists, we're going to also store these as integers because we know that they are integers. We have our first and our second node, not our 1.5 node or something. So we'll just store these as integers. Then 2 nodes. Then we have our n nodes, the number of nodes. We can give a list of our heads, and we don't know the heads of our internal system. So real quick, the equation for the head of a node is just the pressure of the node divided by rho g plus the elevation of the node, right? This is the change of, that would be like the change of heads for a pipe, but for just one node, it would just be pressure over rho g plus its elevation. And we know the pressure and rho g and the elevations of our external heads, but we don't know that for our internal heads yet. So what we'll do first of all is just create a list of zeros, and we'll give it a shape of n nodes because we know we have, we're creating a list of the head of each node here. And then we can say the heads of our external nodes. And then this will be equal to the pressure for each external node divided by rho g plus that node's elevation. And so we should get, for our last node, because it has a pressure of 0 for our sink node, pressure of 0 and a elevation of 0, we should still get a 0 for that. But so the heads of our external nodes will be the external pressures divided by rho times g plus the elevation of our external nodes. And so if we were to call that heads list, it should give us a value for the first element in our list, so the head of our 0 node, and it should also give us a 0 for our sink node. And then we haven't updated the internal nodes heads yet, so we don't have a value for those, so they're still going to be 0. So we should have 5 different values, and then we should have a value for the first one that's not 0, and the rest should all be zeros. So we have a value and then 0, 0, 0, 0. So that looks correct. And then we can also define our internal nodes. And what we can do is create a list and basically do the what we can basically do is just create a list of our total number of nodes and then not include our external nodes. So we can start out by creating a list of our total number of nodes and then exclude or minus our external nodes. So exclude the external nodes. And so if this is correct, we should have our internal nodes as being just 1, 2, and 3. And then it's excluding our 0 node and our 4 node. So external nodes 1, 2, and 3. Okay. So now we can make a function that will solve for the net flow, or not the net flow yet, we'll make a function that will solve for the flows of each and every pipe. So we'll call it calc flows. And we need to give the heads for each node. Now we don't know these just yet, but assuming we do, we would want to return the flows for each pipe. And we'll do that by first creating a list for our flows and setting them all equal to 0. So similar to what we did with our heads list, we just had a list of the correct size, set it all equal to 0, and then we'll go ahead and update it later. And we updated it here for the initial, or for the external nodes. We can do the same thing for our flows, so we can make a list of zeros and then update it as we calculate the flows. So we have a flow for each pipe, and then for each pipe or each flow, we can calculate the flow. So first we need to find a delta head, right? In order to use our flow function, we need to find a delta head. Well, that would be equal to the heads of the node that the pipe is going towards, so the 2 node, minus the head at the node that it's coming from. So minus the heads, and then from node. From nodes. And then we can update our flows list by calculating the flow using our flow function. We can give it the delta head that we just found for each pipe, and then give it the parameters that each pipe has. So LD, K, and ED are relative roughnesses. But we need to do it for each individual pipe here, right? So we need to find not just L, but our length of that particular pipe. So we need to use our lengths list that we've defined here, and we need to use just the length of the particular pipe that we're working with in the moment. So we also need to do the same thing for our diameters. We need to do the same thing for our K value, and then our relative roughnesses as well. And then we can just return the flows. So now we should have a list of flows given the heads at each node. If we have a list of flows, then we can find the net flow for each node. So we can say define calc net flow, and then to calculate the net flows, we need flows, right? And we can again create a list of zeros, and we'll call it net Q. So we'll create a list of zeros. So zeros, one for each node. And we can update each element in our list. So we can add in the flow going into each node, and we can also subtract the flow leaving each node. And that would give us a list of the net flows for each individual node. And so we can add to our net flow list, we can add in the flows coming into the nodes, and then we can subtract the flows leaving each node. So we're just going to add the negative flows, right? And then we can return our net flows list. And so we have a function that's giving us the net flows of our internal, or we have a function giving us the net flows of all of our nodes, but we also know that the net flows for our internal nodes has to be equal to 0. And so we can do something similar to what we did earlier. We can define a function that we will drive to 0, and we can then literally just drive the net flows of our internal nodes equal to 0. And so we'll just define a function real quick. So define internal net queue, and we want to return, we'll eventually want to drive the net flows equal to 0, right? And so if we look, well, we have our net flows here, right? So we can just return our net flows, calculate net flows, and then we need the flows, and we specifically want the internal nodes' net flows. And then we also need to update our heads list to give in the internal nodes heads, right? And we know that the head is going to be equal to the pressure of the node divided by rho g plus the elevation. Well, we know the elevation for each node. We know rho g. So the only thing we don't know for our head of the internal nodes is the pressures of the internal nodes. So we can go ahead and first list this equation out. So the heads of our internal nodes are going to be equal to the internal pressure divided by rho times g plus the internal nodes' elevations. And we're given all of these values except for the internal pressures, right? So we need to give our function some internal pressures. Well, how would we find a pressure for our internal nodes? Well, first, we know that if we're driving this equation to 0, right, if we're driving the internal net flows to 0, we need to give it a pressure to vary. So we need a guess for our pressure. We'll call it internal P guess. And if we were to say right here, so in our function, we're calculating the head of our internal node. So we're assuming we know the head. If we know the head, then the pressure is just the head minus the elevation, and then all of that times rho g, and then we would be left with the pressure for our internal node. And so what we can do is make an assumption for our internal head. So we'll say internal heads guess, and we can just assume that it's about equal to the average of our external nodes. So the mean of our external nodes heads. External nodes. And then if we were to plug that into our equation that solves for pressure in terms of head and elevation, we would have a reasonable guess for a pressure to then vary until we get a net flow of 0 for the internal nodes. So the pressure, of course, is equal to the head minus the elevation. So internal heads guess minus the elevations of our internal nodes times rho times g. And we actually need to define this before, oh crap. Our internal heads guess is equal to, again, we're guessing that it's about equal to the average of the external heads. So now we have a initial pressure to then vary And what we can do is we can drive our net flows all equal to 0, and we'll give it our initial guess for our pressure. And then using that initial guess, we can vary the pressure until we have net flows equal to 0. So the function is going to be our internal net flows, and then our guess is, of course, internal P guess. CalcNet. So now it gives us a lot of information, but we really just want this X array down here. These are our pressures associated with net flows of 0 for the internal nodes. So we can just store that as a result, and then if we call result.x, it gives us just the pressures, an array of the pressures. And so what we've done now is we've found the flows for each pipe, we've found the net flows for each node, and then we've also found we've done it while the net flows for the internal nodes are equal to 0. So we found everything we need. We can just display it now. So we can say the calculated flows is equal to, and we'll just use the functions that we've just defined. So calc flows, and then for each flow, we can display where the flow is coming from, where it's headed towards, and then we can actually display the magnitude of the flow. So we can say so where the flow is coming from, and to do this we can call the from nodes list, and then we can show where it's going. So we'll say to, and then we'll call the to nodes list, and then we can display the flow rate. So calculated flows I. So we have the flow rates for our system, and we can see, we'll see this in the next step too, but the flow rate entering our system, so the flow rate from 0 to 1 and 2 is about equal to the flow rates leaving our system, or the flow rates from 3 and 2 to node 4. And so mass in equals mass out for our system, so that just ensures that we haven't really messed up anywhere. And then we can display our net flows as well. So we can say calculated net flows, and we can just bring in our functions we've just defined. Calc flows needs our heads. And then if we want to display the rest of our information for our nodes, say we want to display our pressure, our elevations, we could do that too. So first we could display, or we can make a list for our pressures, and we can just make it a list of zeros and then update them here in a second. So we have one for each node, and then the pressures of our external nodes will be equal to external P, which we've defined way up here. So the pressure of our external nodes is 200,000 pascals and 0 pascals. And then the pressures of our internal nodes are equal to, right here, because this is the pressures associated with internal net flows of 0. So these pressures are our internal nodes pressures. So result dot x. and then we can list out each pressure, each elevation, and each net flow rate for each node. So for I in range and nodes, and then we can list print. We can say we can list the node. And we can say just I, and then we can list the pressure. We'll do the elevation first, so elevation, and then it's just the Z value for that node, and then we can list the pressure. So it would be from our pressure list here, indexed at I, and then we can list the net flow, which is the calculated net flows indexed at I. So calculated net flows indexed at I. So you can see we have nodes 0, 1, 2, 3, 4. We have our elevation, and we have the pressure associated with each node. And then we also have the net flow. So the net flow for our source node is equal in magnitude to the net flow to our sink node. And then we also have our net flows of our internal nodes being basically equal to 0. So thank you for watching, and I hope you learned something.